So this is joint work with Peter Haissinsky and Luisa Paoluzzi. It is work in progress, although we've written up basically what I'm going to say today, so I can show you that if you are interested. But it's an ongoing project, as you'll see. Okay, so what I'd really like to do is understand the boundaries of all Kleinian groups. So, and this is part of understanding all planar boundaries. So there's some famous conjectures, which I'll mention in a moment, but I'm really interested in the simpler cases and what topological information we can get from the boundary, explicit topological information. Okay, so the audience seems somewhat varied, so let me just give you a little bit of review about what the boundary is. So I'm going to have a delta hyperbolic metric space throughout, and I have a boundary which you can just think of, the best example is a boundary of H2 as S1. So it's the endpoints, it's the set of geodesic rays. You can sort of identify it in your mind with the endpoints of geodesic rays from some particular point. And the rays are equivalent if they have finite Hausdorff distance. And there's a topology that I put on these where neighborhood basis at a point is given by rays that follow a particular ray for longer and longer periods of time. That's what this Gromov product gets you. So when this is large, then these points have gone together for a longer and longer time. You can do this explicitly. If you're bored, you can do this explicitly with the free group on 2 generators, for example. Okay, so I had a base point in the previous slide. So the topology of this boundary does not depend on the base point. So and also if the 2 spaces are quasi-isometric, which was mentioned earlier by Vlad, then the boundaries are homeomorphic. So I can talk about, I'm going to consider delta hyperbolic spaces only up to quasi-isometry, and the boundary is still well defined. So now if I have a group that acts geometrically, so geometrically means by isometries, properly discontinuously and co-compactly, then I'm going to identify the boundary of that space. I'm going to call that the boundary of the group. So now it's a theorem that if G acts geometrically on 2 different spaces and they're quasi-isometric. So this means that the boundary of a group is well defined up to homeomorphism. Okay, so I'm going to stop talking about the space and think about the group, but I will be thinking about the group. Okay, so suppose I have a convex-cocompact Kleinian group. So that's a Kleinian group that acts co-compactly on the convex hull of its limit set. So if I have a convex subset, any convex subset of H3 is also delta hyperbolic because if I take 3 points, the geodesic triangle between them is in the original space. So I'm a convex subset of any delta hyperbolic space is again delta hyperbolic. So this is going to act geometrically on this convex subset of H3. And so convex co-compact means exactly that it acts co-compactly on this convex subset of H3. And so its limit set, which is the boundary of that convex subset, is exactly the boundary of the group. So in this case, we get the group structure coinciding with the classical Kleinian group structure. Okay, so those are the groups that I'm going to study throughout this talk, convex co-compact Kleinian groups. So suppose I have a group, so here's some theorems. So Gabay and Casson-Jungries proved that convergence groups are Fuchsian groups, building on work of Tukia. So this tells me that the boundary and a group acts on its boundary as a convergence group. So this tells me that the boundary of my group is S1. So what can I tell from that? I can tell that my group is virtually Fuchsian. Okay, so it's very strong. Okay, and easier theorem is that if my group is word hyperbolic and so whenever I say equals, I mean homeomorphic. So that's what equality is in this talk. So when my boundary is a Cantor set, then G is virtually free because it has more than one ends. It'll split, and I can do this again and again. And by accessibility, I can do this finitely many times. Okay, so in these low-dimensional cases here, you can tell exactly what the group is from the homeomorphism type of its boundary. This is not in general true. There's different groups that aren't quasi-isometric that have homeomorphic boundaries. Okay, so I want to consider some weirder boundaries that are also the boundaries of Kleinian groups, although these pictures are a slight lie. So these pictures, there's nothing to point with. These pictures are made with Kurt McMullen's LIM program. So these circles here are not part of the limit set. They're just used to give the group of Mobius transformations. And the dark part is where is the accumulation set, so that's the limit set. Okay, so these groups are not actually convex-cocompact, although the one on your left could be the limit set of a convex-cocompact group, and it is. The one on your right here has a global cut point. Okay, so this isn't actually convex-cocompact, but it is a limit set of a Kleinian group. Okay, so I want to study stranger limit sets, so I'll be talking mostly about the one on the left. Okay, so let's do this example of some weird things that can occur that are Kleinian groups. So the first type of Kleinian group I'm going to study, so the Cantor set and the circle can be thought of as being made up of Cantor sets. So I can do something a little bit more complicated. So one way I could get a surface is I could take two, so the boundary of this group is going to be a Cantor set, and then the boundary, I could glue another surface whose boundary as a group is a Cantor set together. So this gives me a circle. So I could just take this one step further. Now I'm going to glue another punctured torus right to the same curve. Okay, so this group right here, this is actually a Kleinian group. So this is three. So each of these is a free group of rank 2, and they're all amalgamated along a single copy of Z. So this is a Kleinian group. So to get this to be the Kleinian, a convex-cocompact Kleinian group, so to get the Kleinian structure on here, I'm going to thicken this whole thing up to get a manifold. And the manifold, this is a realization of the manifold in R3. So so this is a box with two holes glued, pushed through it. So there's empty. So that the outside boundary is genus 2. So you'll notice when I thicken this thing up, I get 3 boundary components, each of genus 2. So going around here, I get a genus 2 boundary component, a genus 2 boundary component, a genus 2 boundary component. The outside is one of those genus 2 boundary components. There's the 2 genus holes right through here. These are the other 2 genus 2 boundary components. And then, so when I thicken this up, I'm going to have these 3 thickened punctured tori right here. So one of those punctured tori is, say, this punctured tori is a punctured torus times I. It bounds up punctured torus times I with the right outside of the box here. There's another one over here. I have a punctured torus times I over here, and then there's one in the middle. So this is an example of a Kleinian group, and I'm going to talk about this type of Kleinian group in a minute. This is just like the surface group. It's made up, the boundary is made up of Cantor sets, and like the surface group, we can determine the type by its boundary. Okay, so before I start talking about the details of the different types of Kleinian groups that I want to talk about, I just want to mention an important theorem of Haissinsky. And this says that these groups with these boundaries are already going to be Kleinian groups, although we'll sort of reprove that in the simpler cases using much easier techniques. So he says that suppose I have a word hyperbolic group, and its boundary is homeomorphic to the limit set of a convex-cocompact Kleinian group, and it doesn't have a subset homeomorphic to the Sierpinski carpet. Then G contains a finite index subgroup that is isomorphic to some convex-cocompact Kleinian group. So what I'm going to do today is I'm going to say, oh, not only do you know it's some Kleinian group, I know exactly what kind it is, and you can read that off easily from the topology of the boundary. Okay, did I not say? I didn't say that. Okay. Okay, so the main tool we're going to use today is some work of Bowditch that directly from the topology of the boundary gets splittings of the group, which is really a completely amazing theorem. So part of what I'd like to do is just sort of advertise this theorem because it's so useful as to telling you what the group is from the boundary. So he says there's a canonical splitting of our group. So I have this group, and it's a hyperbolic group, and it has this boundary, and all this information comes from the topology of the boundary. I didn't write that down. Okay, so each group is 2-ended, and each vertex group is going to be exactly one of the following three types. It's either going to be a two-ended subgroup, so virtually cyclic, a maximal hanging Fuchsian subgroup, okay, and so these are the primo examples of maximal hanging Fuchsian subgroups. They're just hanging off by their peripheral subgroups, which correspond to the boundary subgroups, okay, or there's something else. So these are the rigid ones, and these do not have any splittings over Z. And furthermore, the vertex and the edge groups are quasi-convex. Okay. So here is an example of that. So in the next slide, I'm going to tell you, let me just say it in words, and then you can read the gory details. Okay, so how does he get the splittings from the topology of the group? So you're going to get, so Baldich, so gets the splittings, sorry, from the topology of the boundary. Of the boundary of okay. So he divides the limit. So here, this accumulation set here is the limit set. So what he does is he divides the points in the boundary, takes some points that are local cut points. So what's a local cut point? It means that if I remove that point, then a little neighborhood of it is now disconnected. So for example, this point right here is a local cut point, and it's valency 4. So the valency of a local cut point is when I remove that point, how many ends the resulting topological space has. So here's a cut point of valence 4. Here, sorry, local cut point. Here's a local cut point of valence 4, and then it's hard to see, but a lot of these are like index. Those are valence 2. So all the ones in this picture are either index valence 2 or valence 4. Okay. So you get, so they are equivalence classes. Let me tell you what the equivalence classes are before I go back to this slide. Okay, so first of all, you take all your local cut points, and we're going to put them first, we're going to sort them by their valency. So here we have valence 2 and valence 4. And then I'm going to say that the local cut points are equivalent. So two local cut points are equivalent if they're equal, or if they have the same valency. And when I remove those two local cut points, I get the number of pieces left over that is the valency. So if I have two valence 2, I remove them, and I get 2 pieces. So for example, in a circle, all the cut points are equivalent when I remove any 2 of them. So notice each has valency 2, because this, when I remove one of it, it's 2-ended. So and then when I remove 2, it's going to cut the circle into 2 pieces. So those are all equivalent. So here, this is hard to see. Let me show you a different picture. So now that you've heard it, let me tell it to you again, because it's a little complicated. Okay. So now I have these equivalence classes, and the stabilizers of the equivalence classes. So what's the stabilizer of its equivalence class? It's all the group elements. So the group acts by homeomorphisms on its boundary. So the stabilizer is all the group elements that take that equivalence class to itself. Okay, so the stabilizers of these M2 equivalence classes, so they're the ones where when I remove 2 points, it breaks the whole thing up into 2 pieces. Okay, those correspond to the maximally hanging Fuchsian group. Okay, so what he really proves is that these are Cantor sets, and moreover, they're cyclically ordered Cantor sets. Okay, and then the stabilizers of the 2-element Mn equivalence classes, the M2 equivalence classes are the only ones that can be infinite. The stabilizers of the 2-element Mn equivalence classes correspond to the virtually cyclic subgroups. And furthermore, when I have an infinite, when I have this string, when I have this Cantor set that's going to correspond to a Fuchsian group that you can think of as a surface with boundary, then the closure of that equivalence class minus it is contained in the Mn exactly as here, right? So these are going to be the jump points of the Cantor set. So this is going to correspond to an M3 equivalence class for this group. So this is going to be a Z. It's 2-ended. There's going to be 2 points in the limit set, there's going to be this Cantor set corresponding to like this one coming off of here. There's going to be another Cantor set corresponding to this. There's going to be another Cantor set. Okay, and these 2 points, that's where it's hanging off of. And this picture will be repeated all around. Okay, so the closures, you can tell exactly how the subgroup, how these Cantor sets are glued together. Okay, good. Finally have a good picture. Okay, so let's look at what's happening with this one. Okay, so these 2 points right here, see these are both valency 3 local cut points, and they're equivalent because when I remove them both, it cuts my boundary into 3 pieces. So they're equivalent. So by Bowditch, they correspond to a Z subgroup, so an edge subgroup in my graph of group splitting. And here, along here, it's very hard to see, is a Cantor set worth of equivalence. This is one equivalence class, or in here is one equivalence class of valency 2 local cut points. Because notice, if I remove 2 of these, say they're right there, then it's going to break my boundary into 2 pieces. So these are all equivalent. So right along here is a cyclically ordered string, a Cantor set, corresponding to a surface group, again, by Bowditch. He's saying, look, here's a surface group right here, a Cantor set, and it's a surface group. And it's hanging onto this Z by this set, by these endpoints right here, by its closure. So here I have these 3 Fuchsian groups, and they're hanging, so they're all Cantor sets, so they're free, and they're all hanging onto the boundary. They're all hanging onto this copy of Z right here. And then this picture is repeated over here. So like these 2 local cut points of valence 3 are equivalent. Notice that when I remove them, it breaks it into 3 pieces. Whereas these 2 are not equivalent. Okay, because it doesn't break the boundary up into 3 pieces. Yes?
Why is the Cantor set cyclically ordered rather than just like linearly ordered?
Well, there's a cyclic order. He gets a cyclic order from a circle. So this is actually part of a circle. So linearly ordered is fine because it goes through infinity, yeah. This picture is actually on the 2-sphere.
But so the equivalence class, the one he's entering, is it a circle or is it a line?
It's a cyclically ordered Cantor set. So it's a Cantor set that can be embedded in the circle so that you have a cyclic order on it. So a line is fine because it's a Cantor set. There's a point missing anyway. It's not going to give you a whole circle.
Oh, okay.
It's a Cantor set. So linearly ordered is like ordered on a line is the same as ordered on a circle for a Cantor set because you're missing lots of points. Okay, is that sort of okay? Okay, so now, let's try to understand these groups that are just made out of Cantor sets, and in a particular way, made out of Cantor sets that are surfaces. So a graph Kleinian manifold is a convex-cocompact Kleinian manifold. So it's the quotient of a convex-cocompact Kleinian group. So it admits a decomposition along essential annuli so that each piece is either a solid torus or an I bundle over a compact surface with boundary. And furthermore, the intersection with the annuli is exactly the boundary of the surfaces times I. So this is commonly called a book of I bundles. Okay, so we like to call it a graph Kleinian manifold because it's a Kleinian manifold, and if you take its double, the double is a graph manifold. So if I double along the boundary, it's a graph manifold, where the annuli are going to double to be the tori that cut the cipher fiber pieces up. Okay, so suppose I have a hyperbolic group whose boundary is homeomorphic to the boundary of a graph Kleinian group. Then G is virtually a graph Kleinian group. Okay, so this is exactly like the surface situation, although it's easier to prove. Okay, so let me just go over the proof real quickly because it's not very difficult. I have no idea what time it is. Okay. Okay, so suppose I have this hyperbolic group and it has a homeomorphic, throughout equals means homeomorphic. So it has a boundary that's homeomorphic to the boundary of a graph Kleinian group. So think it has a boundary homeomorphic to something like that. Okay, so what does this mean? This means in the Bowditch decomposition that there's no rigid vertices because this splitting comes just from the topology of the boundary. The splitting is going to be exactly the same, and the pieces are going to be exactly the same. I'm going to have a bunch of hanging Fuchsian groups stuck together along these virtually cyclic groups. Okay, so this means that G has some splitting into this means maximally hanging Fuchsian and virtually cyclic groups, and the exact same graph of groups decomposition as my group K that I knew was graph Kleinian. Okay, so that means it's composed, group theoretically, as these virtually Fuchsian groups hanging onto these virtually cyclic groups. So I want to make that actually a manifold. So what I need to do is and then remember I mentioned in the theorem of Bowditch that all these groups are quasi-convex. Okay, so, and they're all free. So by Wise we can make this makes a quasi-convex hierarchy, actually a very simple quasi-convex hierarchy, and he proves that means that these subgroups are separable. So I can get a finite index subgroup where everything fits. First of all, everything is the virtually Fuchsian groups are actually Fuchsian, and the groups glue together nicely. So I want to have the degrees of the gluing to the tori be 1, so I don't have things wrapping around. So then I can actually make it out of surfaces with boundary times I glued together along tori. And we can see that. So it uses two pretty big theorems, but other than that, the proof is pretty simple. Okay, so what I really want to talk about is what happens when I don't just have hanging Fuchsian groups stuck together in some way. So what if I have a rigid vertex? And I'm going to restrict myself to the case where everything is still a free group and still some interesting stuff can happen. Let me see if I have my example here. Okay, so this is horrible terminology. It's like some kind of bad drink name, but it's called a mixed free Kleinian group. So a mixed free Kleinian group. So I'm going to have a one-ended Kleinian group. It's going to be convex-cocompact, which I didn't put here. And I want its Bowditch composition to have both rigid pieces and hanging Fuchsian pieces. And I want the rigid pieces to be free. So it's very restricted. And I'm going to see if we can tell this exactly from the topology of its boundary. And it's still a little tricky. Okay. Okay, so suppose I have one of these that's a mixed free Kleinian group. Then G is a mixed free Kleinian group. Okay, so how can I tell this? So so again, I can pull off the hanging Fuchsian pieces exactly from Bowditch. So I'm not going to worry about those anymore. I'm only going to worry about the rigid pieces. Okay, so O'Toole has this really amazing theorem that says if G, so it doesn't have to be rigid. If I have a free group with a boundary of Cantor set, and I have a collection of words in it, such that this is what I'm going to do to the Cantor set. I'm going to take my Cantor set, and I'm going to take my finite collection of words, and whenever I see a conjugate, the endpoints of the conjugate of one of these collections of words, I'm going to identify the endpoints. So one way to think of this is, suppose I have so it doesn't actually have to be this situation, but suppose I have a surface which boundary, and then I have these words that are corresponding to the boundary. So actually, let me. So I'm going to think of it, I'm just going to do this case. So now I've got a surface times I, which is a handle body, so it's a free group. And I've got a boundary component. I'm just going to do one word for simplicity. Okay, and then my, so this is a free group, so it's going to have boundary of Cantor set. And there's going to be some, this corresponds to some word in my free group. And the conjugates of this word are going to be some elements up here. So you've probably seen this picture before. So now I'm going to take all those elements, all those pairs of points that are the endpoints of conjugates of this collection of words. I only have one word in this situation, and I'm going to identify them. Okay? So in this case, if I did this, I'm going to get a circle for their boundary. But he says, oh, and suppose you get something that's planar. okay, you do this and you get something that's planar. In this case, I get a circle, it is planar. Then that means that you could realize your free group as a group of a handle body. Okay, so now this is a solid handle body. And your words are a collection of embedded curves on this handle body. Okay, so why is that helpful? Okay, so suppose I have, okay. So why is that helpful? So now suppose I have a group whose boundary is homeomorphic to one of these mixed free Kleinian groups. I've got this rigid piece in my original one. It came from a Kleinian group, so there's that's free, so there's a handle body, and I glued some stuff onto it. Okay, so that means when I pinch those curves, I get something that's planar. So in the other boundary, which is exactly homeomorphic, when I pinch the corresponding curves, I get something that is also planar. So that means that this must have come from some kind of manifold construction by Otal, specifically some handle body with some curves on it, and then I'm going to glue the other hanging Fuchsian groups to it.
Just a question.
Yeah.
When you say on the handle body, you mean on the boundary of the handle body?
Yes. Where did I say? Embedded curves on the boundary of the handle body. Thank you. That should be boundary of the handle body. Thank you. Okay. Okay, so there's still something that we can't tell. So we can tell. Yeah.
The curves on the handle body, can you go back to the previous transparency?
The curves on the handle body. So I have this collection of words in my free group.
No, you said gamma represents a collection of embedded curves on H. So here is your H. You just drew a handle body.
That's right.
So where are the gammas?
The gamma are some curves corresponding to this word. So there's some embedded curves. So I have a word in the free group, and I have a handle body with that same group. A word might be some immersed curve on the boundary if I drew it on the boundary. But he says, no, it's an embedded curve on the boundary. Okay, and if I pinched the corresponding elements up here, if I identified them, I get something planar, then that means these curves here are embedded, which means I can glue something to it and make a manifold, which is what's important to me. Okay, so now we know that we have a Kleinian manifold group, and we know that it's made up of these free pieces. But there's two really essentially different types of handle bodies with curves on them, even if it's all embedded. There's surface groups and non-surface groups. So if I have a genus 2 handle body, so this is now glued in, and I have 3 curves on it. I messed up. I'll try again. I might mess this up again. I'll do it one more time. A, B, you know what? Okay. Okay, so here's a solid handle body with 3 curves glued on it. So it's hard to tell from this picture that this is actually a surface group, but it actually can be realized as a surface, okay, because this 3rd curve here is a commutator. So this is like the generator A and B. This 3rd curve is a commutator, so I can realize this as so I can realize this curve as a commutator. So this is realized as a punctured surface times I, where the punctures are amongst these curves. Okay, so here's this curve, and then I can think of, and now these 2 curves, one will be on the surface times 1, and one will be on the surface times, one will be underneath here, the surface times 0. So let me draw another example. So that's a surface group. So it can be realized as a cyclically ordered. So if I did this construction that I just talked about with Otal, I'd actually get a cyclically ordered Cantor set here. Okay, so this is a hanging Fuchsian group. It might look like this is a rigid Cantor set, its boundary, but actually it's cyclically ordered. And that's what's hard to see sometimes. Okay. Okay, so let me give you an example of this. So here's the ABC example. Here's this group done again. So very similar to the simple example I started out with, where I had three punctured tori times I glued together along a single solid tori. Now I'm going to take this punctured torus times I. So again, I have punctured torus. This is going to be made completely out of free groups, made out of a punctured torus times I. I'm going to glue some hanging Fuchsian groups to all the curves indicated here. So I'm going to glue a punctured torus times I to this component, to this top, times to the curve, the A curve times 0, and the B curve times 1. So you can see maybe that B under here. So here's this picture right here. So I'm going to take this solid handle body, and I'm going to glue hanging Fuchsian groups to it along these curves. Does this make sense how my construction's going? It seems like it's not that much more complicated, but it's almost infinitely more complicated than the one I just did. Let me draw a better picture of it. So I'm going to take let me see if I can use the same colors that I'm using here. So I'm going to glue something hanging out this way. So there's going to be a hanging piece here. There's going to be a free group right here. There's going to be a free group hanging. Let me get the other chalk. There's going to be a free group hanging right here. So this is going to be the part that's rigid. And then there's the other one, this green curve. Okay, so there's going to be these three flappy things going on here. Okay, this is actually, this piece here is rigid. So note, in the Bowdish decomposition, I can cut off this piece. I can see this. It'll be a hanging Fuchsian group. This piece will be a hanging Fuchsian group, and this piece will be a hanging Fuchsian group. So this piece that's left over is rigid. That means there's no more splittings. So let me try to convince you of that fact, that this piece right here is a rigid free piece. So it's a free group, but it's rigid. Okay, so I'm not going to be able to pull it out, and it's a surface group, but I can't pull it out via Bowdish because there's no more splittings. Okay, so this, so if I take my, so how am I going to prove that it doesn't have any splittings? What I'm going to do is I'm going to double it along its boundary, not along these annuli that I glued things to. So when I double this whole manifold that I have here where I glue all these pieces together, I'm going to get some Seifert fiber pieces, which I can cut off, and then I'm going to get this rigid piece. And this rigid piece is actually, the double of this rigid piece is a Borromean ring. So if I have this green, so I've got a, so I'll glue this all together and I get a punctured torus times S1, okay, because when I glue that punctured torus, and then it's going to have removed the AA curves, say right here, and I'm running out of colors, and say the B curves. Okay, so the double of this piece right here is the Borromean rings, and it doesn't have any splitting, so this piece doesn't have any splitting. So that's a rigid free piece. Okay, so suppose I have a rigid free piece. What I'm going to do is I want to, so what is this? So in this case, so this isn't really that great a picture, although it maybe will help convince you that it doesn't have any splittings. What I want to do is I want to take it and I want to pinch those curves to be parabolic. And because it has no splittings, I'm going to get a manifold with totally geodesic boundary. So I'm going to go from a rigid free piece to a manifold with totally geodesic boundary, although it will have parabolics. Okay, and what I like about that is when I have that structure, it's going to be made of round circles. Its limit set is going to have round circles. So I'm going to have, let me just draw this terrible schematic picture here. So I have a punctured torus times I. And I'm going to pinch this curve on the surface times 1 to infinity to a parabolic, and this curve on the surface times 0 to infinity. And so I'm going to have this handle body that now has this structure with totally geodesic boundary on it, and has these two boundary components, each of which are 3 punctured spheres. Okay, when I cut this torus along this curve, and I pinch it, I'm going to get a pinched 3 punctured sphere that's totally geodesic, and another pinched punctured sphere that's totally geodesic. It's still a free group, so these things were studied in Indra's pearls, where they took these free groups and they put structures on them so that their limit sets were round circles. It's a really beautiful theory. If you know more about it, I'd love to talk to you about it because I don't think a lot has been done since then. And so this is a free group, has totally geodesic structure, and so this is a rigid totally geodesic structure. All right. Okay, so in this particular case where we have A, B, and the commutator of A and B all being parabolics, you can solve the equations and see that this is what you get as your limit set. So it's rigid, what you get here. And in this case, we get the Apollonian gasket. For this, that's just for this particular example. In general, we'll get something which is a bunch of round circles, but which is still the limit set of a free group. Okay. Okay, so now I want to see how much I can tell from the limit set, and actually I'm still not completely sure. This is still partially unanswered, as you'll see in a minute. And I want to talk about a mixed Kleinian surface group, and that means that I have rigid pieces and hanging Fuchsian pieces, but the rigid vertex groups are surface groups, okay, which I cannot see that via Bowditch. Okay, so Bowditch cannot tell me whether a rigid piece is a surface group because it doesn't have any more splitting, so there's no more local cut points. Okay, so suppose I have a hyperbolic group and I have a mixed Kleinian surface group and it's quasi-isometric to G. So this is a priori stronger than having homeomorphic boundary in this situation. Then I can say that G is a mixed Kleinian surface group. In particular, the rigid pieces are surface pieces. And it actually follows from this last statement that each rigid subgroup is commensurable to the corresponding rigid subgroup of the original group that I knew what it was. Okay, does that statement sort of make sense? Okay. So let me just outline that for you. Although it's getting late, I'll still outline it for you. Okay, all right. Okay, so I've got a, so what am I'm just going to look at my rigid subgroups. Okay, it's a stabilizer of a Cantor set. So because the boundaries are homeomorphic, once I cut the boundary up into the pieces that came from the topology, all those pieces are still homeomorphic. So I still have the Cantor set as a boundary of my rigid piece, so that means it's free. The edge groups are conjugates of some collection of curves. Okay, because when I pinched them on the one that I knew what it was, I got something that's planar. When I pinch them in the new one, I know that it's planar. So O'Tall's tells me that there's a handle body with that fundamental group and some embedded curves on it. I don't know if they come from surfaces or not, but I have a 3-manifold with embedded curves on it. Okay, so now I know that my rigid group is quasi-isometric to the old rigid group, because remember I was assuming quasi-isometric, where the edge groups go within a bounded distance of the edge groups on the other side. So I have these Z's that are they're in correspondence. Okay, so then we use this to prove, and that this is a non-trivial step here, that the structures where I've pinched them, so we just stick on some horoballs, some combinatorial horoballs, and show that these structures which are horoballed are quasi-isometric to the other one. Okay, so now I have these two. So when I pinch them, so neither of them have any splitting. So when I pinch either of them, I get something with round circles. Okay, and so these are called Schottky sets. And I know that the limit sets of these structures are quasi-symmetric because they're quasi-isometric as groups. So Bonk, Kleiner, and Margankov say whenever I have a quasi-symmetric map, then it's actually a Mobius transformation taking one to the other. Okay, and then you can show, so now I have a Mobius so I can assume that those limit sets of those totally geodesic structures are exactly identical. I can just conjugate so that one is the other. And then I can look at the group of all the transformations of that, and that's discrete, because if I had something getting closer and closer to the identity, it would fix 3 of the circles. So that would mean that it was actually the identity. So that group is, so those groups are commensurable. The rigid groups are commensurable, which implies if one is a surface and the other is a surface. Okay, one last theorem. Do I have time for one last theorem? Master? Yeah, okay. So suppose I have a group that's hyperbolic and the boundary is homeomorphic. Now I just have homeomorphic to that exact group, the ABC group. Then it's a mixed Kleinian surface group, and the rigid pieces are commensurable with the rigid piece of this ABC. But that's because it's exactly the Apollonian gasket. And the Apollonian gasket has this remarkable property that any two, if they're homeomorphic Apollonian gaskets, and they're actually conjugate. There's really only one Apollonian gasket. Okay, so I don't know or even think that these other things will have that property. Okay. So let me just end with, okay, so there's still a remaining question, which I haven't written out here as a question. And that's, can you always see, so is it possible to have 2 mixed Kleinian groups? So it's completely made out of Cantor sets with some rigid pieces where one of them has a surface structure and one of them doesn't have a surface structure. And so that would require having an example more complicated than this, for example. And it would mean that, so first of all, they wouldn't be quasi-isometric by that theorem that I just said. So that would mean there would be 2 Kleinian groups which have homeomorphic boundaries, but which are not quasi-isometric, which we have already with Sierpinski carpets, but this would be a different example of that. And it would also mean that there's a surface in there that we can't see via the topology of the boundary, which I think would be fairly interesting. And I think that's probably the case, that once you get more complicated examples, you can't tell what's going on with the topology. The Apollonian gasket is very special. But I want to say one thing about all the possible boundaries that can occur. So you can talk about, you really shouldn't read this slide. You should just think about trees. It's much easier. So how are these limit sets, how are boundaries made up when they have cut points? What you do is you take the various limit sets of the subgroups and you stick them together along their boundaries. And that's exactly what's happening here. So Sviatkowski, and this is part of a paper in which he uses this to construct hyperbolic groups that have all different various types of interesting boundaries. So he says, okay, I'm going to have a tree system of metric compacta. So I have some tree, which is going to correspond to the Bass-Sayre tree of my graph of groups decomposition and the examples I was talking about. And then for each vertex, I'm going to have some associated compact metric space, which we'll think of as the limit set of that subgroup, or the boundary of that subgroup. And then for each so for each edge in my tree, there's going to be another non-anti-concept subset, which for us will just be 2 points. So it'll correspond to that Z splitting. And a homeomorphism that glues that, so that's a way of gluing these 2 compact subsets along that edge group. Okay, and I want them to, so that I don't want to have a whole bunch with big diameter. So that just makes it work out, the last thing. Okay, so that's called a tree system of metric compacta. And so if you have, so then you can use this to say, okay, then if you have the same data for a tree, it's like the same tree in the same spaces, then their sets are then those spaces are homeomorphic. So now we can classify the boundaries of Kleinian groups up to homeomorphism. Okay, so suppose we have a boundary of hyperbolic group and it's planar. Okay, so then it's going to be the limit of a tree system of metric compacta. So this is using Bowditch. So either it's the 2-sphere, so there's a trivial tree, or it's the Sierpinski carpet. So it's planar but doesn't have any cut points. Or it's all cut points, that's the circle. Or it's not connected. Okay, but in the other case, we're going to have Bowditch's thing. So we're going to be able to have a cut point, and that's going to, so if we have a local cut point, this is going to give us a splitting of the group, and this is going to give us, we'll be able to start to build our tree system of metric compacta. And all the pieces will look like these pieces here. So it's complicated, but it's not undoable to understand all of them. And I will stop now, no matter what time it is.